Scientists just discovered a way to make gravity red 0.00 ms2 for exactly 1.0 second. And the number shows up in more than one place, which makes no sense at all. But it doesn't stay trapped in a lab. It spills into spaceflight math because a 1-second gravity blink nudges every orbit prediction you trust. Every photon hitting a telescope tonight starts its journey before your entire family tree exists. However, a single second of wrong curvature changes where that telescope points next. According to Einstein, gravity doesn't pull. It bends space-time, so turning it off sounds like unplugging geometry. But picture a racetrack made of rubber. The track curves the path, and the cars follow it. Now flatten the track for 1 second, and the cars keep moving anyway. However, the consequences only show up when you hit play again and everything tries to reconnect. For 6 months, a joint team at JPL and an ESA exoplanet group pushing toward Plato's 2026 readiness keeps trying to explain the 0 second away, but each fix creates a new contradiction. First, they blame a timing bug. However, independent atomic clocks disagree by less than 1 nanosecond, so the bug has nowhere to hide. Then they blame Earth noise, but seismic stations show no matching wave in the 0.110 Hz band, and the blink still lands on the same timestamp. Then they look at the data one last time. But the part that scares them isn't the zero, it's the shape of the return. If this isn't a clock glitch and it isn't an earthquake, what exactly turns gravity quiet for 1 second? The answer lands in the overlap. The blink appears in 3 different systems that never share hardware. A superconducting gravimeter shows the local field drop. A laser interferometer shows a matching strain-like hiccup, and a satellite orbit fit suddenly needs a meter-level correction to close. Here's the crazy part. The event length doesn't wander. It locks to 1.0 second, as if something times it on purpose. But then, the physics starts fighting back. Gravity can't switch everywhere at once because changes in gravity propagate at light speed, not magic speed. So a global blink implies a wavefront, and that implies a source. However, no known mass movement can shove spacetime that hard without leaving a scar on the planet. The math points to a stranger option. Not moving mass, but changing the rule that tells mass how to curve space. If a rule changes for 1 second, what does your body notice first? Your stomach, your blood, or the floor? The first consequence hits navigation. Guidance systems assume smooth curvature, and a spacecraft at 7.66 km/s doesn't need much time to miss a target when the curve under it changes. The second consequence hits every accelerometer-based device. For 1 second, down becomes a rumor, but your phone still tries to compute it anyway. The third consequence hits mission planning, because a 1 second uncertainty inside a 400-kilometer-high orbit writes new risk into every rendezvous window and every docking corridor. But the part that hooks the engineers isn't the danger, it's the repeatability, because repeatable anomalies become experiments. Not everyone agrees, and the skepticism sounds sharp for a reason. Dr. Mara Keene at the Caldera Institute of Physics says, "Gravity doesn't blink. Instruments blink. Your job is to catch the eyelid." However, the team counters with the only weapon that matters, timing, and the timestamp lines up across continents like a fingerprint. If the fingerprint is real, what else prints at the same instant? One signal refuses to cooperate, and it shows up where nobody expects drama. At exactly 02:17:18 UTC, a deep underground detector logs a tiny burst of high-energy particles, but the direction solution points nowhere clean. The gravity blink and the particle blip share the same second, however they refuse to share a story. If something pings Earth for 1 second, why does it also toss particles like a calling card? That question drags space back into it, because timing in the sky acts like a lie detector. Plato, on the calendar everyone watches in 2026, times star-dimming events down to seconds and punishes bad gravity models. It turns thousands of stars into clocks you can't hack with a loose cable. But if a 1-second distortion exists, it can show up as a shifted shadow edge in a transit light curve, and that makes the sky a witness. So before the next data set lands, lock in a prediction. Question 1 for the comments. If gravity stops for 1 second where you live, what fails first? Your balance, your building, or your GPS? And here's a poll. Gravity off for 1 second or double gravity for 1 second? Which one scares you more? Because your instincts tell you the story. However, the math tells you whether your instincts survive. Now run the thought experiment for real. Gravity stops for 1 second everywhere you are. The first thing you lose isn't weight, it's contact. Your shoes stop pressing into the ground because the normal force depends on gravity pushing you into the surface. But your body keeps its sideways speed from Earth's rotation, which reaches about 465 nres at the equator, and that sideways speed doesn't ask gravity for permission. You don't rocket into space, however you also don't fall, because a single second only removes about 9.81 meters s2 of downward acceleration, not your planet. In a normal second, gravity drops you by about 4.9 me if nothing holds you up. This second, the fall counter reads 0, so you float, just long enough to feel your stomach climb into your throat. But the floating hides a deeper problem inside Earth, because Earth spends its entire life under its own squeeze. If you don't slam into the sky, what inside the planet moves first when its own weight disappears? Earth carries a mass of about 5.97724 kg, and gravity compresses it like a permanent invisible vice. Gravity stops, and the planet begins to relax outward. However, rock doesn't flow like water, so the release turns into stress. Stress doesn't need minutes, it needs margins, and many faults already sit near their breaking point. Deep inside, the core runs near 5,400 degrees, and pressure shapes how it convects, so a 1 second pressure holiday nudges flows you never see, but the surface still collects the bill. You feel almost nothing in that first second, but infrastructure hates almost nothing. Towers, bridges, and cranes all carry loads designed around constant downward force. Remove that force for 1 second, and the structure doesn't simply rest. It springs microscopically. However, the springback starts oscillations that don't stop when gravity returns. If the ground doesn't hold you down, what happens to the things the ground holds up, like oceans and air? The ocean sits on Earth because gravity gives pressure a direction. Turn gravity off and pressure still exists for a moment, but up and down stop meaning what they used to mean. Water begins to expand and redistribute because its internal pressure no longer stacks neatly, and the message "gravity is gone" propagates through the ocean at the speed of sound in water, about 1/500 ms, so the adjustment starts fast. But the surface doesn't rise like a bathtub filling. It ripples because basins, coastlines, and currents carry momentum that suddenly loses a preferred direction. Ships feel the sickening part first. Buoyancy depends on a gravity field, so for 1 second, floating becomes meaningless. The boat doesn't sink like a rock. It simply coasts while the water stops acting like a cushion. Then gravity returns. However, the return is not gentle, because billions of tons of water relearn down all at once. If buoyancy dies, what does your own blood do when up and down disappear? Your inner ear measures acceleration, so gravity stopping feels like an elevator cable snapping, without the actual drop. Blood usually fights gravity in your legs, but now the fight pauses and pressure equalizes in ways your vessels never practice. You don't explode because 1 second is short. However, you can get a micro-jolt of fluid shift that spikes nausea in the sensitive and disorients anyone already moving fast. Air changes too. Convection needs buoyancy, so heat and smoke stop rising and start forming strange, stagnant blobs. Here's the crazy part. The atmosphere doesn't stay wrapped around Earth by habit. It stays wrapped by gravity. The instant the lock opens, the atmosphere begins its own slow drift outward, and even though 1 second isn't enough to peel the sky away, it is enough to ring the system and launch waves that keep moving after gravity returns. If air starts to drift, what happens above you, where satellites live on constant falling? Orbits exist because forward and down cooperate. A satellite moves forward fast enough that as it falls, it misses the ground, and Earth curves away beneath it. Turn gravity off and the curve disappears, so an orbit turns into a straight line for 1 second. The ISS moves about 7.66 kilometers. So in 1.0 second, it travels 7.66 kilometers along its path, but its path stops curving for that second. However, the missed distance is smaller than your gut expects. The missing inward acceleration at ISS altitude sits around 8.7 meters/2, which shifts position by only about 4.35 meters in 1 second. That sounds tiny, but docking tolerances measure centimeters, and only meters becomes the difference between a clean approach and a near miss. When gravity returns, the station doesn't teleport back onto the old track. It continues from a slightly different position and velocity, and that difference has to be cleaned up with fuel. But a bigger motion steals the spotlight, because the entire planet also stops falling around the sun for 1 second. If Earth stops falling toward the sun for 1 second, where does it actually go? Earth orbits at about 29.78 kilometers. In 1.0 second, it moves nearly 29.8 kilometers along what becomes a straight line instead of a curve. That is the scale moment. It's like missing a gentle turn by driving straight for a heartbeat, except the road is in orbit and the heartbeat is 29.8 kilometers of displacement written into celestial mechanics. However, gravity turns back on and Earth doesn't snap to its old orbit like a rubber band. It continues from the new state, and the orbit becomes a slightly kinked version of what it would have been. The Moon, about 384,400 kilometers away, also coasts straight for 1 second. So the Earth-Moon system picks up a microscopic phase error that laser ranging can detect down to millimeters. Tiny does not mean irrelevant. Tiny means measurable. And measurable means the universe just handed you a lever. If the kink is real, how does gravity turn back on without sending a shockwave through space-time? General relativity enforces a speed limit. Changes in gravity propagate at c, about 300,000 km/s. A 1-second event creates a hard radius of influence, a light-second bubble, and anything outside that bubble cannot know it happened yet. So gravity stopping everywhere at once violates the rule, but a wave passing through Earth for 1 second obeys it. However, a wave strong enough to mimic no gravity doesn't look like the gentle ripples detectors chase. It looks like a rewrite of the field itself. Dr. Kenji Rao, the analyst who refuses to laugh this off, says, if gravity goes quiet, space-time isn't whispering, it's holding its breath. That line lands because it points to the real question, not how do you turn gravity off, but what can make gravity cancel itself for exactly 1 second? If something cancels gravity, what kind of thing does that? Mass, energy, or something that doesn't fit either word? 3. Mechanisms fight for the crown, and each sounds impossible until you let the equations talk. Mechanism 1, a scalar field pulse temporarily changes the effective strength of gravity, like sliding g down and then back up. Mechanism 2, an exotic negative energy configuration, cancels curvature locally, but quantum field theory limits how much negative energy can sit still without snapping back. Mechanism 3 feels the most unsettling. A topological defect sweeps by like a crack in the rules, and your region of space-time briefly runs different code. Each option predicts a different fingerprint, timing asymmetry, polarization patterns, and a distance fall-off that a global sensor network can triangulate. But the strangest clue remains the cleanest. It lasts 1.0 second, not 0.2 and not 20, like a ruler gets slapped onto reality. If the event is a passing structure, the duration becomes a size. If it travels near light speed, then 1 second thick corresponds to about 300,000 km of structure along its direction of travel, nearly the distance you can traverse in light time. However, if it travels slower, thousands of kilometers instead of hundreds of thousands, then the structure shrinks, and Earth-based arrays can map it like a CT scan, slice by slice. That turns your guess into an experiment because your guess about speed predicts the object's size, and the size predicts what else it hits next. The next target isn't space in the abstract. It's the one thing we monitor with obsessive precision: starlight. A planet transit is a cosmic stopwatch because the dip in brightness has sharp edges you can time to the second. Plato's 2026 era job is timing, so it turns thousands of stars into a sensor array no lab can match. However, if Plato catches synchronized 1-second timing anomalies across wide sky patches, then the disturbance is big, the wavefront geometry becomes solvable, and the mystery stops being a spooky headline and becomes a trackable object. Question 2 for the comments. If you have to bet, does the gravity blink come from a passing defect, or from our instruments sharing one hidden vulnerability that nobody wants to admit? Drop a simple answer: field pulse, exotic energy, or rule crack, because the next dataset forces one of them to flinch. And when the next 1-second event hits, it either leaves only a number, or it leaves a path across the sky. Next week, the black hole that's eating itself.